All right, let's jump right in. Today, we're taking a journey to uncover the actual genetic code of mathematics. If you're studying real numbers right now, you might think, hey, I already know everything there is to know about basic multiplication. But trust me, today we're going to look at numbers in a totally different light. We are literally going to crack them open and look at their DNA.
So, to kick things off, I want you to try a little thought experiment with me. Since you were little, you've known how to break a number down, right? You know that 4 is just 2 times 2. But what if we think about numbers in reverse for a second? Building them up instead of breaking them down. Imagine you have this massive infinite bucket of prime numbers, 2, 3, 5, 7, 11, and so on. If you just start grabbing these primes and multiplying them together in every possible combination, could you produce absolutely any composite number in the universe?
Well, the answer is a massive, resounding yes. Every single composite number out there can be built just by multiplying prime numbers together. And this brilliant realization brings us to the core of our explainer today. Welcome to the atoms of mathematics. See, primes aren't just these annoying numbers that refuse to divide nicely. They're actually the fundamental, unbreakable building blocks of the entire number system. It's wild how much this perfectly mirrors chemistry. Think of prime numbers exactly like atoms on the periodic table, like hydrogen, oxygen, or carbon. You can't break an atom down into a simpler chemical substance, right? Prime numbers are exactly the same. A 7 is just a 7. You can't break it apart into smaller whole numbers. Composite numbers, on the other hand, those are your molecules. Just like H2O is built perfectly from 2 hydrogen atoms and 1 oxygen atom, a composite number like 14 is a mathematical molecule built from exactly 1 2 atom and 1 7 atom.
Now, the absolute genius who first locked down the formal proof for this concept was Carl Friedrich Gauss. He published it in his famous work, Disquisitiones Arithmetica. Gauss is literally known as the Prince of Mathematicians. He stands right up there alongside giants like Archimedes and Newton. And while the ancient Greek mathematician Euclid played around with an early version of this idea, it was Gauss who laid down the ironclad proof that's sitting in your textbooks right now.
And that proof gives us the formal definition for the fundamental theorem of arithmetic. It states, every composite number can be expressed or factorized as a product of primes, and this factorization is unique. Okay, I know that sounds like a mouthful of heavy academic jargon, but let's translate it. It simply means that every single mathematical molecule out there has one and only one exact recipe of prime atoms. There are no alternate recipes, period. But here's the absolute most crucial part of that rule, the little caveat at the end, except for the order of its factors. Think about baking a cake. If your recipe says to mix flour and then sugar, or sugar and then flour, you're still getting the exact same cake, right? In math, 2 times 3 times 5 has the exact same DNA as 5 times 3 times 2. To keep things nice and tidy, we generally just agree to write our prime atoms in ascending order, from smallest to largest. All right, it's time to put on our lab coats and actually do some mathematical chemistry. Imagine taking a powerful magnifying glass to a massive, complex molecule and watching its bonds break apart. We are going to decompose the number 32,760. Let's find its exact prime DNA. To do this, we build a factor tree. We look at 32,760 and ask, okay, what is the absolute smallest prime atom we can ship off? Well, it's an even number, so let's slice off a 2. That leaves us with 16,380. Still even. Let's pull out another 2. Now we're at 8,090. We can divide out another 2, bringing us to 4,095. Now, it ends in 5, but actually, if we add the digits, they sum to 18, which means it's divisible by 3. So we separate out of 3, getting 11365. Pull out another 3, we get 455. Extract a 5, that leaves 91. And 91 is famously 7 times 13. Look at the bottom of every single branch here. We've hit absolute bedrock. 2, 3, 5, 7, and 13 are all primes. They literally cannot be broken down any further.
So how do we make this a repeatable strategy for your textbook problems? Just follow 3 easy steps. Step 1. Keep splitting your number by the smallest possible prime. Step 2. Stop only when every single branch ends in an unbreakable prime number. Step 3. Group the identical atoms together using powers. Since we found 3 2s, 2 3s, a 5, a 7, and a 13, we write the final unique recipe as 2 cubed times 3 squared times 5 times 7 times 13. Boom. You've just successfully decoded the DNA of 32,760.
Moving right along to our next section, the detective phase. We're solving the zero mystery. Now that you know exactly how to decode numbers, it's time to play detective and tackle example 1 from your chapter. Here's the mystery we need to solve. Consider the numbers 4 to the power of n, where n is any natural number. 1, 2, 3, 100, a million. Is there any possible value of n that will make this massive number end with the digit 0? Take a second to really think about what that's asking. Can you multiply 4 by itself enough times to magically spawn a 0 at the end of your final result? To crack this, we don't just guess. We look at the DNA. Ask yourself, what actually makes a 0? For any number to end in the digit 0, it absolutely must be divisible by 10, right? And what is the prime factorization of 10? It's 2 times 5. Therefore, for any number to ever end in a 0, its prime DNA must contain at least one 2 atom and at least one 5 atom. They both have to be there, no exceptions. Let's break this down step by step on the whiteboard. Step 1, we established our golden rule. To end in 0, we need a 2 and a 5 in the prime factorization. Step 2, let's inspect our suspect, 4 to the power of n. Well, the number 4 is just 2 squared, so 4 to the power of n is really just 2 squared to the power of n, which equals 2 to the power of 2n. Step 3, the verdict. Look at that DNA. It is literally just a giant, endless chain of 2s. 2 times 2 times 2, forever. The prime number 5 is completely missing. And here is where Gauss's brilliant theorem absolutely closes the case. The fundamental theorem of arithmetic guarantees that a number's prime factorization is unique. Because the factorization of 4 to the power of n is made exclusively of 2s, that uniqueness guarantee means a 5 can't just magically sneak in there later on. Since there's no 5, there's no 10. And since there's no 10, the number 4 to the power of n can never end in the digit 0. Case closed. Okay, let's instantly put your new conceptual mastery to the test. In exercise 1.1, question 5 asked the exact same thing, but for a new suspect. Check whether 6 to the power of n can end with the digit 0 for any natural number n. Based on the logic we just walked through, how would you break this one down? Nailed it. You just look right at the base number, 6. The prime factorization of 6 is 2 times 3. So 6 to the power of n is just 2 times 3 to the power of n. You scan the DNA, you see a 2. You see a 3, but once again, there is absolutely no 5. And because of the uniqueness rule, no 5 will ever appear. Therefore, 6 to the power of n will never ever end in 0. See how incredibly easy and logical these proofs become once you actually understand the underlying atomic structure? Armed with this mental toolkit, you are totally ready to crush the rest of exercise 1.1. Your detective missions will involve finding the highest common factor and lowest common multiple just by comparing the prime DNA of different numbers. You'll verify that awesome property where multiplying the LCM and HCF gives you the product of the original numbers. You'll formally prove why big, messy expressions are actually composites. You have the exact conceptual tools you need to completely dismantle all of these problems like an absolute pro. Before we wrap up this explainer, check out this wild textbook example. Take the number 123,456,789. It looks like someone just smashed their keyboard, right? But even this massive number has a completely unique prime fingerprint. If you were to build a huge factor tree for it, it breaks down uniquely into 3 squared times 3803 times 3607. And yep, those last two massive numbers are unbreakable primes. And honestly, this right here is why all of this actually matters outside the classroom. Why do we care so much about prime factorization? Well, did you know that this exact mathematical science, taking gigantic numbers and knowing they have a unique set of prime factors, is the absolute foundation of modern cryptography? Every single time you log into your email or buy something online, the encryption protecting your data relies on the fact that multiplying two massive prime numbers is easy, but factoring that huge composite number back into its original prime atoms is incredibly difficult for computers. The 10th grade math you just mastered is literally securing the entire modern digital world right now. Think about that the next time you see a prime number. Thanks for hanging out with me for this explainer, and keep exploring the DNA of the universe. Hey everyone, and welcome to a real mathematical detective story. Today, we're going to learn how to prove the impossible using pure, unadulterated logic. If you're a 10th grade student, or honestly just someone who is completely fascinated by the hidden machinery of numbers, you are in the exact right place. We're diving deep into Chapter 1, Real Numbers, and specifically, we're going to tackle one of the most famous proofs in all of mathematics. We are going to lock down exactly why certain numbers behave the way they do. So grab your mental magnifying glass and let's dive right into this explainer. So I want you to think about this question for a second. Proving what a number is, well, that feels pretty straightforward, right? But how on earth do you prove what it cannot be? To pull this off, we need a very special investigative technique from our math toolkit, which is detailed over in Appendix A1.7 of your textbook. It's called proof by contradiction. I like to think of it as the guilty alibi technique. Imagine a suspect in a crime gives you an alibi. You say, okay, sure, let's assume your alibi is completely true. But as you walk through their stories step by step, you realize it completely contradicts itself and just falls apart. Because their story broke its own rules, the original assumption that they were innocent must be false. We are going to use this exact same logic, but on numbers. All right, Section 1, the logic of contradiction. Before we start interrogating our numbers, we really need to line up our prime suspects. Take a look at our lineup of suspects right here. We've got root 2, root 3, root 15, pi, and these incredibly long, non-terminating, non-recurring decimals. These, my friends, are our irrational numbers. Now, from your earlier classes, you know that a rational number is neatly packaged, right? It can be written as a simple, clean fraction, p over q, where p and q are integers. But these suspects, they flat out refuse to be boxed into a simple fraction. And our job today is to mathematically prove exactly why they can't be fractions. Moving on to Section 2, the prime divide theorem. To catch our main suspect, we're going to need a solid magnifying glass. In this case, our magnifying glass is Theorem 1.2, which is entirely built on the fundamental theorem of arithmetic. So this theorem right here is absolutely crucial. Let's walk through it step by step. Because honestly, abstract math is really just a simple pattern waiting to be decoded. Step 1, let p be a prime number. Step 2, if this prime number p perfectly divides a square number, which we'll call a squared. Step 3, then p absolutely must also divide the base number, a. I know that sounds a little wordy, so let's ground that abstract rule with some really simple mental math so it clicks instantly. Take the prime number 2. Now, take a squared number like 16, which is of course just 4 squared. Does 2 divide 16? Yes, perfectly. Therefore, according to our theorem, that exact same prime number, 2, must also divide the base number, which is 4. And it totally does. 2 divides 4. This little rule, this is the exact trap we're going to use to catch our irrational numbers. Which brings us to Section 3, proving root 2 is irrational. The stage is set for the main event. We are finally bringing our prime suspect, root 2, into the interrogation room. We're going to start with that guilty alibi technique. Let's assume, purely to the contrary, that root 2 is a rational number. If it's rational, it has an alibi. It can be written as a perfect fraction, a divided by b. And here is the absolute most important part of the alibi. We are assuming a and b are co-prime. That means they are fully simplified. They share 0 common factors other than 1. They are locked tight like a bank safe. Keep that in your head. Absolutely no common factors. Okay, let's guide this through the algebra step by step, like we're writing it out on a whiteboard. We have root 2 equals a over b. We really want to get rid of that square root, so we square both sides. That gives us 2 equals a squared over b squared. Now let's rearrange it by multiplying both sides by b squared. We end up with 2 times b squared equals a squared. I want you to look really closely at that equation. A squared is equal to 2 times some integer. That means a squared is an even number. Or, speaking the language of our theorem, 2 perfectly divides a squared. And do you remember our magnifying glass theorem? If 2 divides a squared, then 2 absolutely must divide a. So since we just proved 2 divides a, we can write a as 2 times some other integer, right? Let's call that new integer c. So a equals 2c. Now let's substitute this back into our earlier equation. We replace a with 2c, so 2b squared equals the square of 2c, which is 4c squared. Let's simplify that by dividing both sides by 2. We get b squared equals 2c squared. Oh wow, look at what just happened here. The math is now telling us that b squared is a multiple of 2. Therefore, 2 divides b squared. And by our trusty theorem, that means 2 also divides b. Boom! And this brilliantly illustrates our massive aha moment. Do you see the trap we just sprung? We just proved mathematically that 2 divides a and 2 divides b. That means a and b share a common factor of 2. But wait a minute, what was their alibi at the very beginning?
The alibi was that A and B were co-prime, meaning they had no common factors. The story completely contradicts itself. And as your textbook perfectly notes, this contradiction has arisen purely because of our incorrect assumption. The alibi is totally busted. Root 2 is guilty of being irrational.
And you know the beauty of this technique? It works as a perfect template. In example 5 of your text, we interrogate root 3. We use the exact same steps. We assume it's rational, a over b, we square it, and instead of finding a common factor of 2, the algebra reveals a shared common factor of 3. Once again, that co-prime alibi breaks down, and root 3 is locked away as an irrational number.
Let's head into section 4, mixing rationals and irrationals. Now that we have firmly proven these numbers are irrational, let's see what happens when we mix our newly proven irrational suspects with completely innocent, well-behaved rational numbers. Let's look together at example 6 from the text. 5 minus root 3. Is this mixed number rational or irrational? Well, we use proof by contradiction again. We assume 5 minus root 3 is rational, meaning it equals a over b. Now watch how we algebraically rearrange this equation. We want to isolate our known irrational suspect, which is root 3, on one side. By just shifting the terms around, we move the root 3 to the right side and the fraction a over b over to the left.
Look really closely at the resulting equation. We get root 3 equals 5 minus a over b. Since 5a and b are all integers, the entire right side of this equation is a neat rational fraction. But the left side is root 3, which we literally just definitively proved is irrational. This is a massive contradiction. The math is trying to claim that an irrational number equals a rational number. That's completely impossible. Because of this glaring contradiction, our first assumption was wrong. 5 minus root 3 must be irrational.
And hey, this exact same contradiction trick works for multiplication too. Check out example 7, 3 times root 2. Assume it equals a over b. We isolate the root 2 by dividing both sides by 3. We end up with root 2 equals a over 3b. Again, the right side is purely integers, making it a rational fraction. But the left side is root 2, a known, proven irrational. Rational cannot equal irrational. Boom, another contradiction.
So, from working through those examples, we can distill a really powerful core rule. Whenever you mix a non-zero rational number with an irrational number, whether you add them, subtract them, multiply them, or divide them, the result gets infected. The final result is always irrational. The irrationality always wins. Keep that rule in your back pocket. It's super handy. All right, section 5, real numbers summary. Let's bring all these concepts together to consolidate everything you've mastered in chapter 1, because you've honestly done some heavy mathematical lifting today. Let's recap. You've started with the fundamental theorem of arithmetic, which gave us that magnifying glass rule that if a prime divides a square, it divides the base. Then you combine that with proof by contradiction, the incredibly cool logic of assuming the opposite and watching it break its own rules. By fusing these two concepts together, you built a rock-solid, irrefutable proof that numbers like root 2 and root 3 cannot possibly be simple fractions. You didn't just memorize a fact from a textbook today, you actually proved it using pure logic. That's huge. So we've successfully closed the case on root 2 and root 3, but I'm going to leave you with a bit of a provocative thought. What about pi? We know it's a suspect, we know it's irrational, but you can't use our simple prime division theorem to prove it because pi isn't the square root of a prime number. So what kind of advanced mathematical detective work is required to finally trap pi? How deep does the irrational rabbit hole really go? Keep exploring, keep questioning the numbers around you, and I'll see you in the next explainer.
Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here today. Listen, we're going to do things a little differently. I'm putting on my veteran examiner hat right now. I have spent years, literally years, with a red pen in hand evaluating Karnataka SSLC math papers. So we're not just going to sit here and review Chapter 1, real numbers, like a standard textbook reading. No way. Instead, I'm going to hand you the evaluator's blueprint. I'm going to show you exactly where marks are won, where they are brutally lost, and what your examiner is desperately looking for the second they glance at your answer sheet.
Here is our game plan, basically your syllabus for maximizing points today. 1. The exam blueprint. 2. 1-mark traps with HCF and LCM. 3. The 2-mark gold mine. And finally 4. Securing those sneaky final half marks. Let's jump straight in.
The exam blueprint. Okay. The very first thing you really need to understand is how the SSLC math exam is actually graded behind closed doors. You know, evaluators are handed these strict official key answers, and we are hunting for highly specific mathematical statements to award you points. It's not just about the final answer. Board exam battles, they are won and lost in tiny half-mark increments. If you miss a crucial step, even if your final answer at the bottom of the page is 100% perfect, my red pen still has to come out to deduct that half mark. So throughout this explainer, I'm going to reveal exactly where we are instructed to award or deduct these specific increments.
Moving on to Section 2. 1-mark traps focusing on HCF and LCM. So, for our first major scoring area, we're targeting those multiple choice and direct 1-mark questions. Now, the absolute crucial thing to remember here is what I call the golden rule formula. It's simple. The HCF of A and B multiplied by the LCM of A and B is equal to the product of A and B. That's it. Examiners absolutely love using this. It's their favorite way to quickly test your understanding of mathematical relationships without forcing you into long, exhausting calculations.
Now, when you are asked to actually show your work, say using the prime factorization method for numbers like 135, 75, and 20, examiners want to see it laid out perfectly clean. Remember the standard rule: finding the HCF requires you to take the product of the smallest power of each common prime factor. Meanwhile, the LCM demands the greatest power of each prime factor involved. Getting that clean step-by-step structure down on paper, that is exactly what secures full marks.
But, man, here is where I see so many students fall apart and lose precious time. The ultimate student trap is manually calculating an LCM completely from scratch using the long factorization method, even when the HCF was already given to them in the question. Just don't do it. The triumph here is recognizing the shortcut. Plug the known values straight into that golden rule formula we just talked about. You're going to arrive at the exact same answer, but you'll save precious exam time for the much tougher sections ahead. All right, Section 3, the 2-mark goldmine, irrational proofs.
Let's talk about a highly predictable question type that you should honestly view as guaranteed points. Take the proof for showing 5 minus root 3 is irrational. When we look at the official board evaluation key for this exact problem, the half marks are lined up perfectly. It is a rigid formula. You get half a mark for the initial assumption, half a mark for rearranging the terms, half a mark for stating the contradiction, and a final half a mark for the conclusion. It's literally 4 beats to get your 2 marks.
Now you might be thinking, well, maybe that was just a one-off grading scheme for that specific year. Absolutely not. If we pull another official key from a different year, say proving 2 plus root 3 is irrational, guess what? The evaluator's rubric is identical every single time. They want the assumption, the rearrangement, the rational versus irrational statement, and the final conclusion. If you provide those 4 exact things, you get your 2 marks. No questions asked. To make this completely foolproof for you when you're sweating under exam pressure, I've deconstructed this proof into a non-negotiable 4-step framework. Just memorize this simple memory aid, ARIC. Step 1, assume it's rational, setting it to P over Q. Step 2, rearrange the equation to isolate the square root entirely on one side. Step 3, isolate and clearly state that the left-hand side is rational, but the right-hand side is not. And Step 4, contradict. Write out the actual contradiction statement. ARIC. You do that, you win.
Okay, please lean in and pay attention here because this is crucial. I have personally had to deduct thousands of marks over the years for these exact mistakes. These are the evaluator mark traps. You are going to bleed points if you forget to state that the denominator Q is not equal to 0. It's an immediate, verifiable deduction. Bam, half a mark gone. You'll also lose points if you skip declaring P and Q as co-prime integers. Failing to fully isolate the root before writing your statement, that's another trap. And finally, if the actual word contradicts doesn't physically appear written out on your paper, I literally cannot give you that half mark.
Section 4, securing the final half mark.
So let's focus on the absolute last step of your proof. Believe it or not, this is the most frequently rushed step by students. They think, hey, I've already done the hard math, and then they just trail off. And it costs them an easy half mark right at the finish line. The official board key specifically demands this exact phrasing. This contradiction has arisen because of our incorrect assumption, so we conclude. Listen to me, you do not need to get creative here. In fact, please don't. The examiner's eyes are scanning your paper very fast, specifically looking for this exact wording to give you your points. As we wrap up this explainer, I really urge you to approach your SSLC math paper differently. Don't just see it as a test of your math knowledge. Treat it as a strategic exercise in point maximization. Give the evaluators exactly what is on their key, and I promise you, they will gladly give you the marks. Stick to the blueprint. But I'll leave you with this one question to think about before you walk into that exam hall. Are you going to leave those easy half marks on the table by rushing your steps, or will you write exactly what the evaluator wants to see? Good luck out there.